All right, so in this video, we are going to derive the C5 character table. And this is going to be quite challenging task for us because two reasons. One, anytime you have C5 symmetry operations, fifth order 72-degree rotations in your point groups, the math gets really complicated. On top of that, we have a point group, a CN point group, which ends up having imaginary characters in it. So we're going to have some quite crazy math developing in this problem, as you'll see, but we'll try to work through it. So the first step is to figure out the symmetry operations, as we always do for deriving character tables. We're always going to have identity. We're going to have that C5, and I won't even bother trying to visualize a molecule here. We're putting hats as the operations notation as a reminder. And then we can, that's a 72-degree rotation. We can do a 144-degree rotation, a C5 3 times, and a C5 4 times. We can't do a C5 5 times because that is equal to identity. It's a 360-degree rotation. And that's all. That's all the CN point groups have. And here's an example of a molecule. Not a common one, but there's going to be that C5 principal rotation axis, really your only rotation axis, and then you just have 4 different rotations. Now, all 5 of these operations are going to be in separate classes. And the reason is because although they appear to be doing similar things, there's no other operation that can interconvert the axis systems that would make these equivalent. So that's the definition. And so like unlike the DN point groups or other point groups where you would pair C5 and C5-4 and C5-2 and C5-3, for the CNs, always going to be in separate classes. So probably best to just kind of know that. But if you're into this deriving character tables. So now that we know we have the identity, we have the classes, these 5 classes, we can go ahead and make the skeleton of our character table. So put the point group of the character table on the top left, and then we're going to have our 5 classes: E, C5, C5-2, C5-3, and lastly C5-4. And the character table rules, the first rule states that the number of columns that you have is equal to the number of rows. So that means we're going to need 5 irreducible representations. So I'll just put them as gamma 1, gamma 2, gamma 3, gamma 4, gamma 5. And at this point, you fill out your gamma 1, which is those ones across the board, totally symmetric rotation. Okay, and then we're going to figure out the values for down here, and these are going to be, you would think, right, that these would have to be ones across the board as well. We'll see in a second, and why would that be? Because we always say the sum of the squares of the rotation of the dimensionality, the character under the identity, is going to have to equal to the order of the point group, which is equal to 5, the number of symmetry operations in the point group. So these are all going to be 1s, and that's actually going to be true, but we're only going to get there once we break up things into imaginary components. So let's instead go and look at different functions, how different functions transform. The first one we're going to look at is z. So I'm going to draw our axis system here. We're going to think about our z vector. And if we do a identity on the we're going to have our C5 there. We do our identity on the z vector. We're just going to get z back. Identity just is multiplying by 1. And we have a 1-by-1 matrix that describes that transformation that takes z into z. We take the trace of that matrix, which is the sum across the diagonal. It's only a 1-by-1 matrix, so it's not very exciting. But we get that the chi of the identity, the character of the identity, is equal to 1. And so that gets us a 1. It's going to turn out to that z is going to transform as totally symmetric. And we can walk through this with one more example, C5, but then I want to get to the 2 by 2 matrices, which are more interesting. C5 is also going to take the z vector and go to z, because you're spinning along the z-axis. So you're just, rotating this head and the tail, but it's still pointing up. So same logic here, and you're going to get chi of C5 is equal to 1. And all these other rotations, it's the same thing. It's just a different angle there that you're rotating by, but still going to have that z vector pointing up. So you're going to get 1s across the board. So your z vector is totally symmetric. Okay, now let's do x, right? So x is going to be a lot more interesting and complicated. So let's draw x vector. And when we do identity on the x vector, we are going to get x going to x, of course. Let's do a C5. When we do a C5, we're going to be spinning that C5 72 degrees. So we're going to go right to there. Not quite all the way 90 degrees to the y vector. That will be 18 degrees away from that point. So we're going to be some combination of x and y that describes this. And we're going to have to use the 2 by 2 rotation matrix. So that's going to be cosine theta, which in this case is 2 pi over 5 if we're talking in radians, and then minus sine 2 pi over 5, and then sine 2 pi over 5, and cosine 2 pi over 5. Okay, so then we take the trace of this matrix, and we get cosine 2 pi over 5 plus cosine 2 pi over 5. It's a sum across the diagonals, and that's going to be just 2 cosine 2 pi over 5. That's how we're just going to leave it like that. So that's a character under here. This, by the way, now that we figured out that x and y transform together, we can put them like this with the parentheses notation. And we know that we have to keep them together for identity. And so we have to write it a 2 by 2 identity matrix with 1s across the diagonal that takes xy into xy. And we take the sum across the diagonal, 1 plus 1. And so chi of the identity is 1 plus 1, which equals 2. So we got 2 right here. All right. And where we're going to get into imaginary numbers in a second is because, earlier we said these all had to be 1s, but we're getting a 2 here. So we're going to have to break this gamma 2 up into 2 components and then have imaginary numbers for all the math to work out with all the other principles of the character table, including like orthogonality of the vectors. But anyway, if we keep carrying on here, if we do a C5 twice, you can see the exact same thing is going to happen. But now we're going to have a different angle that we're rotating by, cosine 4 pi over 5. That's going to be across the diagonal. I don't really need to write the sine terms. And so your chi of C5 twice, 144 degree rotation, is 2 cosine 4 pi over 5. Okay. And then if we keep going here, we'll see a pattern, right? We're going to get pi here of C5 3. We don't have to write out the matrix this time, just to save us some space and time, is going to be 2 cosine 6 pi over 5. And it turns out that cosine 4 pi over 5 is actually equal to cosine 6 pi over 5 if you look at the unit circle. And so we're just going to write this as 2 cosine 4 pi over 5. And that'll simplify things. We'll have the whole character table in cosines 4 pi over 5s and cosine 2 pi over 5s in the end. before the imaginary number part. Okay, C5 4 times, the last operation. Pi C5 4, just following our little pattern here, is going to be, we're going to get cosine 8 pi and cosine 8 pi over 5 and cosine 8 pi over 5 along diagonals. So we're going to get 2 cosine 8 pi over 5. And another one of these relationships, cosine 2 pi over 5, if you look at the unit circle, is equal to cosine 8 pi over 5. So we're gonna be using a lot of different trigonometric relationships here. With the pi over 5s, you can turn them into something like we might be used to with the cosine 60 degrees, cosine 120 degrees, where you have things like root 3s in there, root 3 over 2. Here you'll have root 5s. It's a little messier. We're just going to keep it in this form. But you could in another video on a different point group, I think C5V, I went into square roots of 5, and I think that just made it a little more hectic. But anyway, so we have 2 cosine 8 pi over 5, but we said cosine 8 pi over 5 equals cosine 2 pi over 5. So this character here is 2 cosine 2 pi over 5. Okay, so that's good. We're not going to quite break this up yet. We know there's a problem here with the dimensionality being 2, but we're going to carry on, and actually a lot of this is going to stay the same. So if I'm smart, I won't delete all this. And well, actually no, we're gonna have to delete this. And the reason why is now we have to find well, one way of deriving this is to find another set of functions, or another function that transforms as something else. And so it's always a good idea after you do x, y, and z, if you're looking for other functions. In this case, I know that the answer is going to be pretty complicated. It's good to look at the other d orbital functions, right? We know our d orbital functions are xz, xy, x squared minus y squared, z squared, and xy. So we can think about xz. Xz is not going to generate a new function. And why is that? Because z is all ones across the board. So if we do xz, we know how xz is going to transform. It's going to transform along with with yz. Sorry, xz and yz are going to transform together because that's multiplying by 1. So it's just like multiplying these two together. So we could write here xz, yc. It doesn't really help us. Z squared is also going to be on here because just 1 squared across the board, right? 1 times 1, so we're going to get that. So this is telling us that our other two d orbitals are x squared minus y squared. That's one to try, right? And so let's try that one, or even maybe a simpler one appears to be xy. So why don't we try that? Okay, so if we do identity on xy, we're going to get xy. What happens if we do a C5 on xy? Oh boy. So we have to recall what happened to x, right? And again, this came from this 2x2 matrix where we had, I'll just write the 2x2 transfer rotation matrix that we were using, right? We had, let me write it in a different color to keep our notes separate here. Cosine 2 pi over 5 minus sine 2 pi over 5, sine 2 pi over 5, and cosine 2 pi over 5. Okay. So what this tells us is that x actually goes to, so this was, by the way, right, x times y. So if we evaluate this, multiplication out, it's telling us xy actually goes to cosine 2 pi over 5x minus sine 2 pi over 5y, and y, we're going to multiply it now because we're doing xy, y goes to sine 2 pi over 5x plus cosine 2 pi over 5y. Now we get to FOIL this out. So that's a lot of fun. So let's do the two x terms first. We're going to get cosine squared, cosine, not squared, 2 pi over 5 times sine 2 pi over 5 times x squared. Let's do the y terms next. That's going to be minus cosine 2 pi over 5 sine 2 pi over 5 xy. And then we're going to get the mixed terms here. So there's going to be a minus sign. And I think probably the best way to do this is show it over here. So this is continuation, guys. Sorry. So these two terms and then minus, we're going to have 4 terms here, right? Because we FOIL out minus sine 2 pi over 5 times sine 2 pi over 5 again. I think actually I can fit it. This term over here. Minus sine squared 2 pi over 5 xy. See how that works? This term times this term. And then we're going to have the cosine terms. So that's going to be plus cosine squared 2 pi over 5 xy. All right, so we can factor out some things here. And in particular, what we can factor out is x squared minus y squared. So if we factor out x squared minus y squared, where did we make a mistake here? When we did sine 2 pi over 5 times cosine 2 pi over 5, we should have had this be y squared, right? Because there's 2 y squared terms. Okay, so now we're back in business. So now we can factor out that cosine 2 pi over 5 sine 2 pi over 5. Okay? And so we have that. And we can also, well, we already factored, we can factor out these terms for xy, which is cosine squared 2 pi over 5 minus sine squared 2 pi over 5. Okay, so I'm going to simplify this a little bit more. I'm keeping this x squared minus y squared term the same. I'm just going to carry it over. But this last term, I'm going to do another one of these trigonometric tricks that we have in blue. Let's do it in green. And you may remember that cosine squared of x minus sine squared of x is equal to cosine of 2x. So what that means is for us, cosine 2 pi of 5, that's our x, minus sine squared 2 pi over 5 is actually going to be equal to cosine, there's all these relationships, right? Cosine 4 pi over 5. So that's cool. We can now take out this term and sub it in for something a lot simpler, which is cosine 4 pi over 5. Okay, and so what happens here is what we basically figured out from all this, if we look at it, is that we started with xy, right? That was a d orbital function. We thought that might get us something interesting. We looked at 3 other d orbital functions that didn't get us anything interesting. They get us redundant stuff because we're timesing by z. And we got xy transforming as a linear combination of xy, something times xy, a constant times xy, and another constant times x squared minus y squared. So that tells you that x squared minus y squared and xy are transforming together, okay? And so just like x and y transform together for gamma 2, for gamma 3 now, okay, xy and x squared minus y squared are going to transform together. Because of that, Then we have to write a 2 by 2 matrix, right? And so we have to write our identity matrix for now x squared minus y squared because x squared minus y squared. And we're going to have that matrix transforming xy and x squared minus y squared with our identity matrix, ones across the diagonal. And then we take the character across that diagonal, and we get that the chi, the character of the identity, is going to be equal to 1 plus 1, right, which equals 2. So again, we're going to have a value of 2 here for our gamma 3 that we're deriving. So we did that for identity, right? With xy doing something, x squared minus y squared doing something. For C5, with xy doing something, well, we have to figure out what x squared minus y squared does. So this one, the math is even longer, right? So we know what x does. X goes into, right, up here, right? Cosine 2 pi over 5x minus sine 2 pi over 5y. So let's write that down, and we're going to have to square it. I'm actually going to just know that it's this term here squared, and then we're going to go through and FOIL that out, right? So we're going to get cosine squared 2 pi over 5 x squared. Then we have the sine terms. That's going to be positive sine squared 2 pi over 5 y squared. And then we're going to have these two negative terms that are the same. That's what happens when you square things. You always have the two inner terms being the same. 2 cosine 2 pi over 5 times sine 2 pi over 5, and this is a mixed term, it's xy. So that took care of the x squared component. We have to minus that by y squared. So now this part is the y, right? It came from down here in our rotation matrix. So we have to remember to minus everything here because we have minus y squared. We're going to have sine squared 2 pi over 5 x squared. And then minus, let's do the cosine term, cosine squared 2 pi over 5 y squared. And then we're going to have, again, a minus. We can't forget to minus here. Minus 2, same looking term as we had before, 2 cosine 2 pi over 5 sine 2 pi over 5. This is sine x, y. And now we can combine like terms. So what do we have here? Well, we have here something that it's looking like we have an x squared thing here. So let's factor out an x squared. So we're going to do that by cosine 2 pi, cosine squared, sorry, 2 pi over 5 minus sine squared 2 pi over 5 x squared. And then we have plus, let's factor out a y squared, sine squared 2 pi over 5 minus cosine squared 2 pi over 5, all that times by y squared. So those took care of all the squared terms, and then we have these two same terms here, which combine to give us minus 4 cosine 2 pi over 5 sine 2 pi over 5 x, y. Okay, and then we have to remember that this relationship up here that we wrote. So cosine squared 2 pi over 5 minus sine squared 2 pi over 5. Remember cosine squared x minus sine squared x equals cosine 2x. So that equals cosine 4 pi over 5. So we can simplify this. Cosine 4 pi over 5 times x squared. And if you look at this part, I'm not going to write the x squared yet. I'm going to actually factor this out. If you look at this part, this is just the negative of this, right? So we can factor out actually a negative y squared from cosine 4 pi over 5. So that's how we're going to get x squared minus y squared, which is exactly what we want. We want it as a linear combination of x squared minus y squared and xy, our two functions. And here we already have it as a constant times by xy. So we're pretty good at this point. So now we can write our transformation matrix. And our transformation matrix is going to take our two functions that we know transform together, xy and x squared minus y squared. And all we care about is the on-diagonal elements. So the on-diagonal elements are the coefficient for xy, the coefficient for xy. So it's xy goes in something plus cosine 4 pi over 5 times xy. So this component here is going to be cosine 4 pi over 5. And then this component here, we don't really care about, but if we wanted to write that down, we could. It would be cosine 2 pi over 5 times sine 2 pi over 5. Doesn't really matter. So we're not going to write it down. And then for x squared minus y squared, it doesn't matter because when we take the trace of the matrix, we're not going to be adding up those off-diagonal components. When we look at x squared minus y squared, we do the same sort of thing where we just care about this on-diagonal component, the component that's times by x squared minus y squared. And notice that that's also cosine 4 pi over 5. So things end up simplifying quite a bit. We then take the character, the trace, by summing up these diagonals, and we can say that chi of C5 operation is just going to be equal to cosine 4 pi over 5 plus cosine 4 pi over 5, which equals 2 cosine 4 pi over 5. And so now we know what our character is underneath C5. And you can see this is a unique, it's looking similar to gamma 2, but it's unique, it's different. Before we had 2 cosine 2 pi over 5 for gamma 2. All right, so now, do we have to do all the same work for C5 too? Technically, yes, but it's going to be a lot easier. And the reason why it's going to be a lot easier is because we don't have to rewrite all this stuff, okay? Let's just think about what would happen. What would happen here? Now our transformation matrix here is going to have 4 pi's over 5's. So all these are going to be 4 pi's over 5's. All these are going to be 4 pi's over 5. All these are going to be 4 pi's over 5 until we get to here, right? Where we went from 2 pi over 5 to 4 pi over 5. We use this relationship. So if we were to erase here and put a 4 and 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 a 4, fine, we would get a 4 there and a 4 there. Now this is wrong technically because I didn't erase all the other ones, but you get the idea. And this one would now be 8 pi, right? Because cosine squared x minus sine squared x equals cosine 2x. So we have to make this one 8 pi. So that's then going to change this value to an 8. Okay, and then if we did the same sort of logic for the xy transformation, we got 2 pi's, those are now 4 pi's, 4 pi's. Okay, and where did we do a tricky substitution? It was right here. Cosine 2 squared 2 pi over 5 minus sine squared 2 pi over 5. Those are going to become 4 pi's, right, when we change it. So we're being a little tricky here, but it's going to saves us tons of time. So this becomes now, again, an 8 pi. Again, we have cosine squared 2x minus sine squared 2x equals cosine 2x. That's just one of these trigonometric things. So this becomes cosine 8 pi. But if you remember what we did over here, we had one of these other trigonometric relationships which said that cosine of 8 pi is actually equal to cosine of 2 pi over 5. Sorry, cosine 8 pi over 5 equals cosine 2 pi over 5. So what that means is that this becomes actually 2's. And so then we take the trace along the matrix, and we get the chi for it. Now this is C5 2 is actually 2 cosine 2 pi over 5. So we can plug that in. And again, it's different than what is above. Okay, so now let's do C5 3. And we're going to do a similar sort of trick here. All these 2 pi's now aren't going to become 4 pi's now, but they're going to become 6 pi's. So we have 6 pi, right? Because we're doing a rotation 3 times, so it's 3 times as high. So this became 6 pi, this became 6 pi, and yeah, I guess this would be 6 pi too, but we don't really care, that's off diagonal. The key one is this one, right? So we have cosine 6 pi over 5 minus cosine 6 pi over 5. That turns out to get us what? 12 pi over 5, okay? And 12 pi over 5, and so the same thing is going to happen for down here, right? We're going to get this 8 is going to turn into 12 for the same reasons. It's going to turn into 12 pi over 5 when we had 6 pi. And cosine of 12 pi over turns out to be the same as cosine 2 pi over 5. Well, pi over 5 equals cosine 2 pi over 5 also. Okay, so the character ends up being, so we have, 12 pi here and 12 pi, but that ends up being 2 pi. So it ends up being the same, where we still get 2 cosine 2 pi over 5 for our C5 3 character here. Whoops. Over 5. All right, last one, same sort of logic, but now we're doing C4 4 times. So if one time was a 2 pi over 5 rotation, 4 times is going to be 8 pi over 5 rotation. You go through this cosine 2 pi business when you do the cosine 2x minus sine squared 2x. So that's going to get you a 14 pi. I hope you see the pattern by now, right? So you're going to get 14 pi over 5 plus 14 over pi over 5. Well, cosine, this is all just unit circle. So cosine 14 pi over 5 is equal to cosine of 4 pi over 5. So this one ends up being 2 cosine 4 pi over 5. So that's our last one. So at this point, we can actually assign the Mulliken symbols. And we know the totally symmetric representation is going to be A. We give it a Mulliken symbol, an A or a B. And we give it an A if we're symmetric, if the dimension is equal to 1, so the character under the identity. And we give it an A if we're symmetric with respect to the principal rotation axis, which we are. If this was a -1 here, we would give it a B. And then these two ones are going to be called E's in the Mulliken symbols because they have a dimensionality of 2. The character under E is 2. This E is identity. This E is a Mulliken symbol E. They're different E's. And we're going to call the first one 1 and the second one 2. Sort of arbitrary which one you choose, but people will do it this way for the C5 character table. The Mulliken symbol rules aren't, totally precise in this manner. So Problem is, we're not done, right? And we're not done because we're violating one of our mulliken symbol rules, one of our, sorry, character table rules, our first character table rules, which is the sum of the squares of the dimensionalities, these, 1 squared plus 2 squared plus 2 squared, right? Those are the dimensionalities squared, is equal to, has to be equal to 5, which is the order of the point group, the number of operations of point group. This is not true. Okay, something is wrong with our character table. These functions are transforming like this, but they're going to actually need to be split up into imaginary components. And so we'll do that in the next video.